All right, I think we will go ahead and get started. So welcome to another 4D BGC webinar. We've been holding these webinars for a little while now, and we're trying to move to a more consistent monthly schedule. So keep a lookout for updates about upcoming webinars in the new year. And these webinars are intended to share progress on four-dimensional observation-based products of ocean biogeochemistry. So either how those are developed or how those are utilized to address a number of different scientific questions. So we have a great speaker today, Giacomo Navarra. Uh, we're having some audio issues and testing before, but hopefully he's in a good spot to present. Um, and I'm going to give a quick introduction here before Giacomo gets started. So this webinar series is presented by the SCOR Working Group 168, the 4D BGC Working Group. And so the group's goal is to facilitate discussion and coordination among different scientific communities around developing, validating, and distributing 4D BGC data products. And the ultimate goal is to enhance access and utility of BGC Argo observations through these data products. So one thing I wanted to call out in this introduction is one of our group's contributions so far, which is this online repository of biogeochemical data products that's available on the BGC Argo website. So this page gives a number of different data products, as well as when you click into any of them, a lot of different information about them, their time resolution, spatial resolution, and where they can be found. So it's a great resource if you're looking for observation-based mapped biogeochemical data products. Also, more information about our group can be found on our website with this link here. You can also probably just search SCOR 4D BGC and find this information. We have a schedule for our webinar series, as well as a link to that product archive and a number of different resources on this website. A couple other things, we have a mailing list. That's probably how you heard about this webinar. And you can sign up through a link on our website, which takes you to this Google form and gets you on our mailing list. And also all previous webinars are recorded and posted to our YouTube channel here. So if you miss one and you want to watch it later, you should be able to do that. So with that, I'll introduce Giacomo, who's going to be talking about causality analysis of a positive trend in Southern Ocean chlorophyll-a. And I believe he's using BSaucy, so a map data product based on BGC Argo observations, as well as other observations to do this work. So I will turn it over to you, Giacomo. Feel free to start sharing. And you are still muted, just so you know. Are you there, Giacomo? We can't hear you right now.
Can you hear me now?
Yes, yes, we can.
Okay. Oh, okay. Wait. Okay.
Yep, please take it away. We can hear you. Oh,
Okay.
now we can't see your slides.
Can you see it now?
Yes, now we got
Okay,
it.
great.
All right,
Okay.
go for it.
Well, thank you for this possibility. My name is Giacomo Navarra, and I want to show you some of my work regarding understanding in the chlorophyll and net primary production increase in the Southern Ocean. So just a brief introduction. The Southern Ocean is a very important place, not only because it lacks continental boundaries, but also because of the intense eddy activity presence in the region. This is also taken from this paper here, this figure. Due to this activity, the isopycnal in this region are tilted, so it's not flat. And this weak stratification allow for a deep water mass to upwell at the surface. And this is a very important process because these water masses are usually rich in nutrients, allowing to create a so-called high nutrient, low chlorophyll region. The reason for that is because phytoplankton cannot actually use all these available nutrients, and therefore, because of light and iron limitation. So that's why the name high nutrient, low chlorophyll. Now, understanding this process has been challenging for many years because essentially the lack of data, for example, as you see the panel A in this figure, these are the data available for World Ocean Database for nitrate. And usually then, because of this lack of data, the climate community has relied a lot on model simulation. Like this is the GFDL ESM4 simulation. However, they still have bias, and it's not. We want to find a way to actually improve our knowledge without relying on the simulation. And there are two main problems. One is that physical biogeochemical interaction are very complex, and we don't have a set of dynamical equation to describe the system. Therefore, and also the second one is this lack of data. Now, however, the good news is that in recent years, because of the SOCOM project, the Argo flows, in particular in the Southern Ocean for SOCOM, has increased a lot, which is a good news. And this shows the increase in available Argo flows. And this allowed the first to be possible to use machine learning tools applied directly on the data. And this is a brief overview about how machine learning is getting some attention in climate science. There are three big areas where this actually is happening. One is the reconstructing of observation. So a map like the one I showed before, you take directly the available data and you reconstruct the pattern from the region where you have the data. And the second part here is the parameterization part. So now our models rely for a process which happen below the resolution, you need to use parameterization. But I see in the future that all of this parameterization will be all data-driven, so to make the model more accurate. And then shortwave weather forecasting, so actually to speed up the weather forecasting system. Now, this figure, I wanted to use these are satellite data from ESA, European Space Agency, for the chlorophyll. And this is just to emphasize the problem we wanted to analyze today. And this increase in chlorophyll happening along the Southern Ocean. So you see that this is the mean over the surface ocean from 1998 to 2024. Now, this brings two main questions, which is part one and part two of the presentation. One is actually, can we actually predict this variability? And the second one, so in the first part, we don't consider the trend. It's all detrended. And the second part instead is actually, can we actually use causality tools to explain this long-term trend in chlorophyll? So this is the part one, is that regards improving skill prediction in short-term time series. Now for this part, I use BSOSI, as John mentioned before, is that BSOSI, I want to say something, is that is a state estimation. So we have a physical model, a dynamical model, which is MIT GCM in this case. And the biogeochemistry component is the biogeochemistry with light iron nutrients in nutrient model, Bling model. So in this case, it has like 8 nutrients. It's essentially a simplified version of cobalt. Cobalt has 33 tracers. In this case, we have DIC, alkalinity, iron, phosphate, nitrate, oxygen, and the dissolved organic phosphate and nitrate. So 8 in total. And this is what I've used in this case. Now to show in this part, I'm focusing on a related quantity to chlorophyll, which is net primary production. And also the NPP in the model shows an increase. The simulation, the spin-up period goes until 2012. So until 2012 is spin-up. After that is the real simulation, is the real state estimation. And it actually shows an increase in NPP. And the panel A is the mean over time. So if this is there is still a little bias, but the trend is the same in the state estimation. Now, for my experience, when we try to do this short-term prediction, it's very important not to go to the more complicated method, but to just start simpler and then eventually go more complicated. So with the method that I'm using in this part is a kernel ridge regression. I use as input feature like the temperature, the salinity, the sea ice area, the mixed layer depths, the iron, the nitrate, irradiance, and wind stress curl anomalies. When I say anomalies, this is anomalies respect to the seasonal cycle in the first 100 meter. And the period of the simulation from 2013 to 2020 is the training period, while the remaining one is I use for testing. So when I say this is an important detail, I use this input sequence of 12 months. This is what in the traditional approach you have as an initial condition of a forecast that we usually use a one-time step in a traditional way. Now, our machine learning tools allow you to do longer sequence as input, and you predict a one-time step across all the testing period. So just to visualize the prediction, A, B, and C is the residual. So this is the error. So here at the boundary where you see red color, this is where the model is more uncertain in doing the prediction. And I done up to 19 months lead time. And the E and F is the same, but with the spatial mean. So just to visualize the predicted time series. Now I want to say, when I say lead time here, this is the time from the end of the input sequence to the first prediction. So here the first prediction done 1 month, this 7 months up to 19 months. So now the next step is to actually calculate the scale. So the scale is done in this testing period. Now C is the scale for the kernel ridge regression in correlation. So these are correlation measures for the 1 month lead time. And F, I put here the 7 months lead time case, and I arrive until 19 months in the article. Now, B and E is the comparison where I try to do the same prediction, but with linear regression, multilinear regression. A and D is with the persistence, because the persistence, just to emphasize, is essentially the autocorrelation. So this is you want your skill to be above the one you would get if you simply autocorrelate the NPP, the NPP, so because that's the baseline, and actually is the case it's our case, so that's good. And the next step now we want to see what originates the skill, and this is what I've done here. So this panel A, B, and C, these are 3 sensitivity tests. So essentially, now we wonder if instead of giving all the input sequence, all the input the feature, we select a subsample of it, and we see the difference in the scale. So if we compare, we retrain the model with that just subset of feature, and to see how much the scale difference, in this case, compared to the total model. So panel A, I use only ocean-related variables, so only mixed layer depths, SSH, sea ice, and temperature. Panel B is where I use only the nutrients compared to the total model. So this is the difference between the total model minus in scale with the nutrient only related, and C is with light related only. Now so when you see low value here, it means the model, that subset of feature is actually very good because you can predict the MPP also with this subset of feature. And to better quantify this difference in D, E, and F, I did the mean of this difference. And as you can see, in this mean skill difference is the lowest one compared to the other 2 cases. However, there is actually one thing to notice here, because if you look at the G, H, and I, the standard deviation of this difference, not the mean, it's true that G is lower in terms of standard deviation, but the atmospheric related part has the highest standard deviation, so indicating that the wind stress curl and light have a very regional pattern, as you can see also from here, where you have a great decline in scale near the coast, but in the open ocean, it doesn't decline, it doesn't reduce much the scale. Now, to better show this regional difference, I wanted to plot here the mean of the scale done in 6 different regions of the Southern Ocean. So the Ross Sea, the Indian Ocean sector, the Pan-Antarctic sector, the Weddell Sea in panel D, and the AB sector and the West Pacific sector. So this is essentially the mean scale done calculated from the kernel ridge regression. From the total model is the brown line. From the ocean only model is the blue line, and the green line is the from the atmosphere and light related variable only, and the violet one is from nutrient only related. So as we showed before, the blue line is the nearest to the brown one. So it's you add the lower decline from using only ocean dynamics. But there are some followed by light related, but there are some regional difference because, for example, in the Pan-Antarctic sector, it's clear the decline. But in the West Pacific sector, you can have a way similar scale, but by looking at the green line and the blue line. And while it completely while it completely drop the scale if you use the AB sector. So our conclusion for this part was that this increase in MPP can actually be predicted, but in the ocean dynamics is an important contribution to this, followed by light-related quantities. Now there are limitations in this approach, which I want to emphasize a lot. Now, the excluding one variable and see the impact it doesn't actually lead to real causality, but it actually can give you insight. And is also this method is very dependent on the kernel choice that you do during the cross validation part. So now I want to go in the second part where you actually want to analyze not to do a prediction in time, but causally related to different data set for in this case the trend itself in chlorophyll. Now, this is actually a toy model, just to emphasize a lot again at this point that this methodology in which you actually exclude a variable and then see the impact in the scale might not actually lead to causality. Here I want to say why. Imagine you have a toy model like this, and you want to predict y, that in our case is the chlorophyll. And then you do the prediction like with a linear regression and see the root mean square error. And now you do the same prediction, but excluding X4, for example. You might obtain that X4 play a contribution, but it's not because X4 has a direct link to Y, or because this variable influence another one, which is directly linked. So just to say why excluding one is a limitation. And same would be true if you do with a neural network, because there have been literature in terms of explaining the prediction of a neural network with explainability tools, but you would have the same problem also in this case, because if you run, for example, shapely values on a neural network, and you get that X4 is important, it might not, leading that importance to causality is actually not completely true. So now I want to say these methods that have come out recently. It's called Peter and Clark momentary conditional independence, which actually has been done on purpose to emphasize the relationship, not just the importance of one variable, but also how important is that variable given the presence of others as input. So it's mainly two phases. One, where you see causality as a sort of graph, if you want. You have the graph you can see as the latitude and longitudinal points of your input feature of temperature, SSH, and you initially say don't do any links. So you consider any possible link between all your edges of your nodes, your graph, and the chlorophyll in all the other nodes. Then the algorithm actually exclude the irrelevant links based on a significance they are solved, which you can put it yourself, 95% or 99%. And then on a second phase, these links that has been found in the first one are retested to see how this would change if we actually perturb the input. So is this link gonna be changed if we actually condition these results on the presence of other variable and also different lags? These are the emphasize these two important steps of this PCMCI. So here I have applied it to the chlorophyll, to the increasing chlorophyll happening in the Southern Ocean. And this the first two figure here is the same map I showed you before from the European Copernicus satellite data. In this case, that showed this increase. And here I select only the time period from Bisosi. Now, to better visualize the trend, here I compare the A and B. A is the trend from the satellite data, and B is the trend from Bisosi. And C and D is actually the seasonal dependence of the trend. So as you see, there are some difference with the satellite data, but in the Pacific sector, I see the Bisosi a little overestimated the increase in chlorophyll at the boundary, where it's more uncertain, but not here in the open ocean, and is here near the coast. So just to emphasize this difference. But if you look at C and D, where you look at the seasonal dependence, the Bisosi was able to capture mostly the seasonal dependence of this trend, except in this area here, because I think this is a model artifact. And this is the same seasonal dependence of the trend from the satellite data. Now, once we have this increase in chlorophyll, we want to relate it to phytoplankton growth rate and limiting factor. So panel A is the same increase in NPP, which is actually, has to be a pattern very similar to the one from the chlorophyll. And the phytoplankton growth rate instead is in B. So you see that the phytoplankton growth rate is actually increasing also in a same region here, but also here. And now, why is actually phytoplankton growth rate increasing? This can be related to two limiting factors. One is the light, that in the Southern Ocean, there is this period between March and May, where you have a decline in light limitation. And in the article, we want to emphasize a lot on the iron factor rather than the light, as the iron is way more spread across the year rather than the light. So for this reason, we look into the iron budget in this case. In the iron budget, we have both advection, iron advection and iron diffusion. So we emphasize much more the dependence of the iron diffusion because the advection is actually stronger only in a very localized region of the Southern Ocean. Well, and you see in this case, what you show here is the difference between iron diffusion between the last 3 years of the Bisosi simulation with the first 3 years of Bisosi. So this pattern here is very compatible to what you see from chlorophyll in the Bisosi, rather than this that is instead is way more localized. Now, once we have that, this is the same figure I show for the iron diffusion, but we want to relate this in particular to physical changes. So this in panel B is the same difference in mixed layer depths. So around this region here, you have a deepening of the mixed layer depths and also here. And if you look at the buoyancy frequency, this is the buoyancy frequency and the salinity. Salinity shows this great pattern here, very compatible to the advection of iron presence in this region. So once our hypothesis was that there is not one mechanism which is causally linked to that increase in chlorophyll, but mixed layer depth plays a role. But we expect that it plays a role only in the open ocean, not here where you have this increase in salinity, or here in the Pacific Ocean. So we actually run this PCMCI algorithm, and what you see here is how strong is the causal link. So in the first panel here, this is the causal link between the iron diffusivity anomalies and the chlorophyll anomalies, which shows very great link. And the second panel is in actually the mixed layer depth link to chlorophyll related. And we also include a link with the wind amplitude. And now we can see that actually this relation of the mixed layer depth and wind amplitude has linked with chlorophyll, but mainly in the ACC region. We explain this in the paper by saying that you have a situation where you have more iron mixed at the surface because of the deepening of the mixed layer due to the change in the winds. And now this is true for this region, but we also have done this for the salinity and the chlorophyll. So the salinity in particular shows a link in this region where we didn't see for the mixed layer depths. So the Indian sector is very particular, and also this one, however, here I'm more skeptic because the mod, as I showed the comparison with satellite, this was more not related to what the observation shows. While in this part here of the Indian Ocean, it said advection process count way more for that increase in chlorophyll. So these methods can actually be very useful, not only to see what pattern is important, but also to emphasize regional difference in terms of explainability. So these are my conclusion. So the chlorophyll is actually shows a positive trend all over the Southern Ocean. Understanding the variability and how predictable it is a very crucial step. And also relating the improving our causality knowledge, like with method like PCMCI, is a useful approach not only to identify the more important predictor, but also regional difference. I want to close with this takeaway message. I think in the future, more and more integration will happen between data-driven model and machine learning model and ocean biogeochemistry. However, this integration, doing just skillful prediction is not enough, because we want a machine learning model to do not to do the right prediction for the wrong reason. And the wrong reason here, I mean that it doesn't do an accurate prediction because it finds a physical mechanism, but because it finds a spurious analog. Therefore, investigating these causality tools is a crucial step. And thank you. I'm happy to take any question.
Thanks so much, Giacomo. That was great. So we will open up the floor to any questions. So feel free to raise your hand or type something in the chat. And while folks are thinking, I just have one, I guess, relatively simple one, perhaps. But I noticed there was a pretty large difference in magnitude between the satellite chlorophyll, both the trend and the absolute value, and the value of the chlorophyll concentration.
That is true. We have found that.
Do you know what the reason is for the difference between that and B-Saucy?
I think the reason is that in the Bisosi they underestimated zooplankton grazing, so they should actually increase it. The probably that I think that is the reason.
Got it. Okay. All right. I'll pass it over to Guillaume.
Hi, Gian. Thanks very much, Gian, for your talk. Super neat work. I had a question regarding one of your slides when you showed these sort of Hofmöller plots of NPP, light growth, and iron limitation.
Oh yeah, wait. This one.
This one. Yeah,
Yes.
okay. So that's for the entire Southern Ocean, right?
This for the entire Southern Ocean, the
Okay.
surface in this case.
Okay, surface. So my question is that your panel D, when you
Yes.
have, so it's ion limitation. So does red mean that it's more limited in ion?
Yes, in this case, yes.
Okay, so could you comment on why you observe an increase in NPP and an increase in the
Right.
growth rate, even though you got lower light and more ion limitation during the growth season?
No, wait, C is the lower light limitation. So more
Oh,
light in the
oh yeah.
more light. C is so
Ah,
blue
okay,
is
got
lower
it.
light limitation. However, this is a good point, I think that you bring up because I for what I see here is that you have this increase in light limitation even if you have more iron. Because if you do the same plot for the concentration of iron, you will see also an increase. So I think what is happening is that there is more iron, but it's also more limiting because it's diffused way more.
Okay, and so do you think that maybe this reflects a change in sort of phytoplankton community that is more
I
adapted to lower light?
I think it reflects changes to cell size, so they adapted to use less iron, less
Yeah,
and also to
it's
actually
more
to
light.
more light.
Yeah, it's more like, not less light. Yeah, yeah. Okay, got it. Cool. Thank you.
Any other questions? I have another one I can ask too. I'll go ahead and read one that was just posted in the chat from Jin. Okay, if we can discover causal relationships, how can we use this relationship to enhance the predictability of machine learning? And feel free to
Okay.
unmute if you want to clarify anything with this question.
So the question is how the causal related they used to improve predictability. So these are two different problems. Improve predictability is depends a lot on the data that you have, but in improving causal relation is it's more related to which quantity you use as input to your model or the time length of your time series. So this understanding in I want to say how can this be used like not just for the short time scale but for the long time scale. So if you see that if you have from your causal analysis that one quantity mixed layer depth, for example, is very important, you might say for the climate model community that the having mixed layer depths very accurate can improve predictability also for climate simulation of biogeochemistry. Was that a good answer?
Yeah, I think so. I'll go ahead and ask my other question I had, which was you noted a salinity trend that
Oh,
correlated with
yes.
chlorophyll. Do you have any sense for what's causing the salinity trends or the salinity differences?
Yes, we noticed for that for this salinity pattern, I was more confused for some time because it seems very localized in this region. Instead, chlorophyll increase also in other part. I think this part here of this the panel D, this part here where you see a decline, I would not relate this to chlorophyll. But here instead, given the fact that this region here also show an increase in advection of iron, I would say I would relate this physical mechanism to the increase of chlorophyll here, but just here in this part here.
So do you have a sense for the physical process that's causing that salinity change?
So in this case, you have that if you have more salinity, you decline your buoyancy frequency also decline. So it actually becomes less stratified here in this case, and that can lead to more chlorophyll.
All right. Any additional questions?
I think I might have another one, John.
Yes.
So bouncing back on that, so as you said, is the pattern that you observe are pretty localized.
Right.
Is there a way to quantify if there could be any effect of sea ice export on this? Because that would probably impact the freshening of your
Yes.
surface and subsurface.
No, to quantify the effect of a sea ice covered area for this. Uh, I think one way in which to quantify is that this pattern, mixed layer depths and sea ice are very seasonal. So this is the general importance over the whole region, but looking at this causality depending on the season that you're looking is, I think it would be a good way to quantify it.
Okay.
All right, last call. Okay, seeing nothing, I think we'll thank Gian Giacomo again. Really interesting presentation. And look out for an email from us for our next webinar, which will be after the new year. We haven't set it on our schedule yet, but we will be in touch. So thanks for coming, everybody.
Thank you.